Let knowledge flow like a river, without any hindrance. Don't make it like a stagnant pool. Hello, friends and young engineers. Welcome back to Structural Design Only, a channel with a different vision. I am P.S. Chatterjee. Today is August 11th, 2026. A very happy birthday to your channel. Our journey started on August 11th, 2020, with a simple aspiration, to share my acquired skills and knowledge with a community of educated viewers. I have tried my best along the way, often without knowing where the performance would lead. Borrowing the words of my beloved poet, Rabindranath, my heart desires to give, not merely to receive. I don't know when or where I will stop. It is simply like this, no stop before the full stop. Let's start our new journey with part 3 of the strapped footing design. Today, we are going to escape the complexities of eccentric footings subjected to biaxial moments. And instead, we will land on a much more stable solution, the strapped footing. The title of today's video is, Strapped Footing with Bi-Axial Moments, Excel Automation, Part 3. In this session, I will demonstrate exactly how to develop a dynamic, professional-grade dashboard in Excel for strapped footing design under biaxial moments. Most importantly, I covered all the fundamental theories behind strapped footings in Part 1. I also explained why this approach is superior to relying on extreme, eccentric footing designs. And I also explained all the Excel formulas required for Chapter 1 and Chapter 2 in Part 2 of this series. Once again, I must say, you will be among the luckiest structural engineers if you encounter and solve this specific type of problem in your lifetime. So, you may ask, why should we learn the design of a strapped footing? That is a very natural question. We learn this technique because it will uplift your skills enormously, helping you to tackle other difficult designs with ease. So, without wasting any more time, let's jump straight into the core of the issue. Before we begin, however, if you appreciate the effort behind this work, I have a small favor to ask. Please show your support by hitting the like button, sharing this link with your fellow engineers, and subscribing to Structural Design Only for more technical content. Don't forget to click the notification bell so you never miss an update on my upcoming videos. This resource is free, yet it provides insights that often go beyond what you learn in college. Sometimes, it is much more. Your support is what allows me to keep creating these deep dive tutorials for our professional community. I am doing this for the love of the craft, not for money. Now, let's get started. This is the slide for our strapped footing with biaxial moments, Excel Automation, Part 2. Where we paused our last journey. Today, we will start our journey by explaining Chapter 3 of the design sheet. Here, we are going to see the Excel formulas for the design of pedestals P1 and P2. Before diving deep into Chapter 3, I have to say, I have taken a shortcut. Here, I used the maximum load on pedestals P1 and P2 for our design. Because, from a concrete and steel consumption point of view, these pedestals will be minimal. Let's start our new journey. Once again, we are seeing that cells A29 to E29 are filled with a dark gray color. Here, we have to put our inputs. On the screen, we are going to see the defined names of these cells, and they are as follows. Cell A29, bar_dia_col, for the longitudinal bar diameter. Cell B29, bar_no_col, for the number of longitudinal bars. Cell C29, B_X_col, for the width of the pedestal. Cell D29, D_Z_col, for the depth of the pedestal. Cell E29, H_col, for the height of the pedestal. Next, we are going to see the input check for pedestals in cell E31. The defined name of the cell is input_check_pedestal. It is the starting point of the design for pedestals. Presently, we are seeing check, because all the input cells of Chapter 3 are blank cells. The Excel formula for this cell is, if strap_beam_check is not equal to OK, this cell will remain blank. If strap_beam_check equals OK, and any of the input cells are blank, then Excel will type here check inputs. Otherwise, it will type OK. Now, we are going to see the Excel formulas for the calculation of the area of steel, percentage of steel, check for steel, and net concrete area. For these formulas, once again, Excel will first check input_check_pedestal. If it is not OK, the cells will remain blank. Otherwise, it will calculate the area of steel, percentage of steel, and net concrete area as per standard practice. So, I am not going to recite these Excel formulas. Now, on the screen, we are seeing the Excel formula for the check for steel. Excel will first verify input_check_pedestal. If it is not OK, the cells will remain blank. Otherwise, it checks whether the percentage of steel provided falls within the acceptable range, between a minimum threshold of 0.2% and a maximum of 4%. Since here, a pedestal acts primarily as a heavily loaded compression member under biaxial moments due to the eccentricity of load on it, we have configured our custom check to target a minimum percentage of 0.2% and a maximum limit of 4%. Of course, depending on your specific design requirements, you can adjust these thresholds to suit your project needs. Now, on the screen, it is the Excel formula for the load on pedestal P_U. In cell G28, we are going to type this formula. The defined name of the cell is PU_COL. Excel will first verify input_check_pedestal. If it is not OK, the cell will remain blank. Otherwise, the value of P_u will be the maximum absolute value of Ru_1 and Ru_2. Next formula on the screen is the formula for M_U_X in cell I28. Once again, Excel will first verify input_check_pedestal. If it is not OK, the cell will remain blank. Otherwise, it will calculate the moment due to eccentricity along the x-axis as per IS 456. The defined name of the cell is MUX_COL. The calculation is PU_COL multiplied by the maximum of B_X_COL divided by 30, and 20, divided by 1000, to convert the dimension from millimeters to meters. Now, on the screen, it is the formula for M_U_Z in cell K28. The defined name of the cell is MUZ_COL. This formula is similar to the previous one, except that instead of B_X_COL, we use D_Z_COL. Next formula on the screen is the formula for P_U_Z in cell G29. The defined name of the cell is PUZ_COL. P_U_Z is the design load that a pedestal can withstand safely. Once again, after verifying input_check_pedestal, it calculates the value of P_U_Z as per IS 456. Next formula on the screen is the formula for M_U_X_1 in cell I29. The defined name of the cell is MUX1. M_U_X_1 is the design moment along the x-axis that a pedestal can withstand safely. Once again, after verifying input_check_pedestal, it calculates the value of MUX1 as per IS 456. Now, on the screen, it is the formula for M_U_Z_1 in cell K29. The defined name of the cell is MUZ1. This is also the design moment along the z-axis that a pedestal can withstand safely. Once again, after verifying input_check_pedestal, it calculates the value of MUZ1 as per IS 456. The next formula is the formula for alpha_n in cell F31. The defined name of the cell is alpha_n. I have already explained what alpha_n is, in part 1 of this series. After verifying input_check_pedestal, it calculates the value. If PU_COL by PUZ_COL is less than or equal to 0.2, the value of alpha_n will be 1. If it finds PU_COL by PUZ_COL greater than or equal to 0.8, the value of alpha_n will be 2. If it finds PU_COL by PUZ_COL in between 0.2 and 0.8, the value of alpha_n is 1 plus, within brackets, PU_COL by PUZ_COL minus 0.2, whole divided by 0.6. Now it is time for the interaction ratio and its check. Presently we are seeing the formula for the interaction ratio. We have to type this formula in cell G31. The defined name of the cell is I_R, or interaction ratio. After verifying input_check_pedestal, to get the value of I_R, it calculates 2 times mux_col divided by mux1 to the power of alpha. Finally, the Excel round function will provide us the value of I_R up to 3 decimal places. Now, on the screen, it is the formula for the check of the interaction ratio. In cell H31, Excel's formula for this check is very simple. Once again, after verifying input_check_pedestal, if Excel finds I_R less than or equal to 1, then it will declare the interaction ratio as OK. Otherwise, it will say check. The defined name of the cell is interaction_check_pedestal. Now we are at the last line of Chapter 3 for the dynamic pedestal design. On the screen, it is the formula for the overall check for pedestal design, spanning the merged cells from I31 to K31. The defined name of the cell is pedestal_check. As usual, after verifying input_check_pedestal, if Excel finds it OK, it checks the interaction ratio check. If it finds that OK as well, it will output OK. Otherwise, it will say check. With this, following the pedestal design, we are shifting our focus to Chapter 4, the design of the left-hand pad footing, F1. Now, in this slide, we are going to see the formulas for the left-hand pad footing F1 of the strapped footing. Once again we are seeing the cells A36 to G36 are with dark gray color. Here we have to put our inputs for the footing, F1. On screen, we are seeing the defined name of the cells, and they are as follows. Cell A36, LX_F1, length of the footing in X direction. Cell B36, LZ_F1, length of the footing in Z direction. Cell C36, bar_dia_X_F1, diameter of the bars along X direction. Cell D36, spacing_X_F1, spacing of bars along X direction. Cell E36, D_F1, overall depth of the footing F1. Cell F36, bar_dia_Z_F1, diameter of the bars along Z direction. Cell G36, spacing_Z_F1, spacing of bars along Z direction. Now, on screen, we are seeing the formula for input check for footing F1 in cell F43. Defined name of this check_4. In this formula first Excel will check pedestal_check, if it remains not OK, cell will remain blank, otherwise, it will check the above inputs and if it finds any input is missing, it will say provide inputs, otherwise it will say OK. Now, on screen, In cell B37, we are seeing the formula for the calculation of self-weight of the footing F1. Defined name of the cell is S.W._F1. In this formula, first Excel will check _4, if it remains not OK, cell will remain blank, otherwise, it will calculate the self-weight of F1, by Lx_F1, multiplied by Lz_F1, multiplied by D_F1, multiplied by unit_WT_conc, divided by 1000. This division of 1000 is to convert the overall depth from millimeter to meter, and unit_WT_conc is the unit weight of concrete in kilonewton per meter cube. Now, we are seeing the formula for area of steel provided in X direction for footing F1 in cell D37. Defined name of the cell is AST_PROV_F1_X. First Excel will check _4, if it remains not OK, cell will remain blank, otherwise, it will calculate the area of steel provided in X direction of F1, by 1 plus, round down value of whole number of 1000 divided spacing _X_F1, multiplied by 0.25 times pi, multiplied by square of bar_dia_X_F1. Now, we are seeing the formula for percentage of steel provided in X direction for footing F1 in cell F37. Defined name of the cell is PT_PROV_F1_X. First Excel will check _4, if it remains not OK, cell will remain blank, otherwise, it will calculate the percentage of steel provided in X direction of F1, by rounding the value up to 3 decimal, 100 times AST_PROV_F1_X divided by 1000 time of D_F1. Here 1000 is the 1 meter width of the footing F1. Now, we have to calculate the area of steel provided in Z direction for footing F1 in cell I37. Defined name of the cell is AST_PROV_F1_Z. This formula is more or less same as the calculation of AST_PROV_F1_X. The only differences are, instead of spacing _X_F1, it will be spacing _Z_F1, and instead of bar_dia_X_F1, here it will be bar_dia_Z_F1. Now, we are seeing the formula for percentage of steel provided in Z direction for footing F1 in cell K37. Defined name of the cell is PT_PROV_F1_Z. Once again, this formula is more or less same as the calculation of PT_PROV_F1_X. The only difference is, instead of AST_PROV_F1_X, it will be AST_PROV_F1_Z. And since it is a pad footing, D_F1 will be same for both direction. Now, we are seeing the formula for the working load case for footing F1 in cell H36. The defined name of the cell is load_case_C1. First, Excel will check _4. If it is not OK, the cell will remain blank. Otherwise, it will calculate the value by taking cell B9 minus 100. In cell B9, we have the factored load case number. The working load case is required for calculating the safe bearing capacity for load cases other than the dead load plus live load combination. Next, we have the formula for the working pedestal load on P1 in cell I36. The defined name of the cell is P_1. First, Excel will check _4. If it is not OK, the cell will remain blank. Otherwise, it will calculate the absolute value of RU_1 divided by 1.50, if load_case_C1 equals 101, or 1.20 otherwise. We adopt this approach because we need to convert the factored load into a working load. Finally, we add the self-weight of the footing F1. Now, we are seeing the formula for the area provided for footing F1 in cell J36. The defined name of the cell is area_PROV_1. First, Excel will check _4. If it is not OK, the cell will remain blank. Otherwise, it will calculate it by multiplying LX_F1 with L_Z_F1. Our next formula is the formula for the area required for footing F1 in cell K36. The defined name of the cell is area_req_1. First, Excel will check _4. If it is not OK, the cell will remain blank. Otherwise, it will calculate the required area by dividing the working load by the SBC using a coefficient. Here, SBC is the safe bearing capacity of the soil. If the value of load_case_C1 remains 101, this coefficient will be 1. Otherwise, it will be 1.25, as per the recommendations of IS 1893, the Code for Earthquake Analysis. One thing I need to mention here is that if Excel finds the value of area_req_1 greater than the value of area_PROV_1, then cell J36 will be filled with a yellow color, the text will have a strike through, and the font color will turn red to indicate an insufficiency in the area provided. Now, we are seeing the formula for the calculation of two-way punching shear and its check for footing F1. The calculations for punching stress are in cells A40 to D40, and in cell E40, we are going to check the calculated punching stress against the allowable punching stress. The defined name for cell A40 is D_EFF_F1. It is also known as the effective depth. First, Excel will check _4. If it is not OK, the cell will remain blank. Otherwise, it calculates the overall depth of the footing minus the clear cover minus half of the maximum bar diameter along the X and Z directions. The defined name for cell B40 is VU_punch_F1. It calculates the punching shear force. In the Excel formula, Excel will first check _4. If it is not OK, the cell will remain blank. Otherwise, it will simply put the negative value of RU_1. The defined name for cell C40 is A_punch_F1. It calculates the punching critical area. In the Excel formula, Excel will first check _4. If it is not OK, the cell will remain blank. Otherwise, it will calculate 2 times B_X_COL plus D_Z_COL, plus 2 times D_EFF_F1, the whole multiplied by D_EFF_F1. Next, the defined name for cell D40 is TV_punch_F1. It is the calculated value of the punching shear stress. In the Excel formula, Excel will first check _4. If it is not OK, the cell will remain blank. Otherwise, it will calculate 1000 times VU_punch_F1 divided by A_punch_F1. Finally, we will check this calculated TV_punch_F1 against the allowable TC_punch_allow. In the Excel formula, Excel will first check _4. If it is not OK, the cell will remain blank. Next, it will check if TV_punch_F1 is less than or equal to TC_punch_allow. If so, it will type OK. Otherwise, it will type check. Now, we are going to calculate the one-way shear check for footing F1 in the X direction, covering cells F40 to J40. In cell K40, we will check this one-way shear stress in the X direction. Let's start with cell F40. Now on the screen, it is the Excel formula for cell F40. The defined name of the cell is RU_F1. In this formula, Excel will first check _4. If it finds _4 as a blank cell, this cell will remain blank. Otherwise, it will calculate the value of RU_F1 simply by dividing negative RU_1 by the multiplied value of LX_F1 and L_Z_F1. Here, the multiplied value of LX_F1 and L_Z_F1 is simply the area of pad footing F1. Next, we have the Excel formula for cell G40. The defined name of the cell is L_EFF_X. It represents the effective length of footing F1 in the X direction. In this formula, Excel will first check _4. If it finds _4 as a blank cell, this cell will remain blank. Otherwise, it will calculate the value of L_EFF_X by taking 0.5 times LX_F1 minus 0.5 times the sum of B_X_COL plus D_EFF_F1, with the entire quantity by 1000. Next, we have the Excel formula for cell H40. The defined name of the cell is VU_max_F1_x. It represents the maximum shear force near the column face of footing F1 in the x direction. In this formula, Excel will first check _4. If it finds _4 as a blank cell, this cell will remain blank. Otherwise, it will calculate the value of VU_max_F1_x by multiplying RU_uplift_F1 by 0.5 times LX_F1 minus 0.5 times the sum of B_X_COL plus D_EFF_F1 divided by 1000. Our next target is cell I40. The defined name of the cell is TV_cal_F1_x. It represents the calculated shear stress of footing F1 in the x direction. In this formula, Excel will first check _4. If it finds _4 as a blank cell, this cell will remain blank. Otherwise, it will calculate the value of TV_cal_F1_x by dividing the value of VU_max_F1_x by D_EFF_F1. Next, we have the Excel formula for cell J40. The defined name of the cell is TC_allow_F1_x. It represents the allowable shear stress of footing F1 in the x direction. In this formula, Excel will first check _4. If it finds _4 as a blank cell, this cell will remain blank. Otherwise, it will calculate the value of TC_allow_F1_x by checking the value of FCK. If FCK is less than or equal to 40, the value will be 0.85 times the square root of 0.8 times FCK, multiplied by the square root of 1 plus 5 times beta_F1_x minus 1, with the entire numerator divided by 6 times beta_F1_x. If FCK is greater than 40, the formula uses 40 instead of FCK. As per the IS code, the value of TC_allow_F1_x remains constant and is capped at the value corresponding to an FCK of 40. Now, we are on the final point of the one-way shear check for footing F1 in the x direction. Yes, it is the final check between the calculated shear stress TV_cal_F1_x and the allowable shear stress TC_allow_F1_x in cell K40. The defined name of the cell is shear_check_1_way_F1_x. The Excel formula for the cell is structured such that Excel will first check _4. If it finds _4 as a blank cell, this cell will remain blank. Otherwise, Excel will check whether TC_allow_F1_x is greater than or equal to TV_cal_F1_x. If the condition is satisfied, it will type OK. Otherwise, it will type check. Now, it is time for the one-way shear check for footing F1 in the Z direction. We are going to perform this calculation in the cell range from A43 to E43. On screen, we are seeing the defined names of the cells. After close observation, we find that these names are more or less the same as the one-way shear check for footing F1 in the X direction, except that in place of _X, we have _Z. By copying these cells and pasting them into this table, we only need to adjust the defined names. Since the formulas use the same types of defined cell names ending with _Z, I am skipping this portion from the detailed explanation and moving on to the calculation of bending stress in the next slide. Now, in this slide, we are going to calculate the bending stress check for footing F1 in the X direction, within the cell range from G43 to K43. Let's start from cell G43. The defined name of the cell is mu_F1_X. Here, we will calculate the value of the ultimate bending moment per meter run for footing F1 in the X direction. You may ask, why bending moment per meter run? Yes, because we considered the width of the footing as 1 meter as per standard practice. The Excel formula for this cell is structured such that Excel will first check _4, if it does not find _4 equal to OK, this cell will remain blank. Otherwise, Excel will calculate 0.5 times RU_uplift_F1 multiplied by the square of L_EFF_F1_X. Now, it's time for cell H43. The defined name of the cell is mu_BD_2_X_F1. Here, we will calculate the value of the ultimate moment divided by BD_2, or the bending stress parameter, for footing F1 in the X direction. Once again, the Excel formula will first check _4, if it does not find _4 equal to OK, this cell will remain blank. Otherwise, Excel will calculate the value by taking 1000 times mu_F1_X divided by the square of D_EFF_F1. Next is the formula for XU by D in cell I43. The defined name of the cell is XU_D_X_F1. It represents the calculated value of the neutral axis depth ratio from the top compression fiber. The Excel formula will first check _4, if it does not find _4 equal to OK, this cell will remain blank. Otherwise, Excel will calculate the value by taking PT_PRO_F1_X divided by 100, multiplied by 0.87 times FE, with the whole term divided by 0.36 times FCK. After calculating this value, Excel rounds it up to 3 decimal places. Now, it's time for cell J43, representing the percentage of steel provided. This cell has no defined name. Once again, the Excel formula will first check _4, if it does not find _4 equal to OK, this cell will remain blank. Otherwise, the value will be equal to PT underscore PROV underscore F1 underscore X. Here, PT underscore PROV underscore F1 underscore X is the value of the percentage of steel that we calculated earlier in cell F37. Next is the formula for the required percentage of steel to counter the bending stress in cell K43. The defined name of the cell is PT underscore REQ underscore X underscore F1. In this formula, Excel will first check underscore 4, if it does not find check underscore 4 equal to OK, this cell will remain blank. Otherwise, Excel will calculate the value of the percentage of steel required. To understand how this works, let's look at the Excel function maxa, which finds the largest value among its arguments, treating any logical values or text appropriately. After checking the primary condition, Excel evaluates whether mu underscore bd underscore 2 underscore x underscore f1 is less than mu underscore lim underscore bd underscore 2. If it finds the logic to be true, it calculates the steel percentage using the quadratic equation, 100 times negative k underscore 2, minus the square root of k underscore 2, squared minus 4 times k underscore 1, times mu underscore bd underscore 2 underscore x underscore f1. With the entire numerator divided by 2 times k underscore 1. It then compares this calculated number with 0.12, which is the minimum percentage of steel required to counter minimum bending stress, using the maxa function. Finally, Excel rounds up the resulting value to 3 decimal places. Now, it is time for the bending stress check for footing F1 in the Z direction. We are going to perform this calculation in the cell range from A46 to E46. These calculations are more or less the same as the bending stress check for footing F1 in the X direction, except that in place of underscore X, we have to place underscore Z. By copying these cells and pasting them into this table, we only need to adjust the defined names. Since the formulas use the same types of defined cell names ending with underscore Z, I am skipping this portion from the detailed explanation and moving on to the checks for footing F1 in the next slide. Now, it is time for the overall checks for footing F1 across the cell range from F46 to K46, covering the footing area, two-way shear, one-way shear, bending in the X direction, bending in the Z direction, and the overall design check. Let's start with the footing area check in cell F46. The defined name of the cell is area underscore F1 underscore check. In this formula, Excel will first check underscore 4, if it does not find check underscore 4 equal to OK, this cell will remain blank. Next, it will check area underscore PROV underscore 1. If it finds that area underscore PROV underscore 1 is greater than or equal to area underscore REQU underscore 1, it will say OK, otherwise, it will say check. Next checking is for two-way shear in cell G46. Defined name of the cell is punch underscore check. Here, Excel will first check underscore 4, If it does not find check underscore 4 equal to OK, this cell will remain blank. Next it will check punch underscore shear underscore F underscore 1. If it finds punch underscore shear underscore F underscore 1 is OK, it will say OK, otherwise, it will say check. Next item is check for one-way shear in cell H46. Defined name of the cell is underscore 1 underscore way underscore shear underscore check. For this check, Excel will first check underscore 4. If it does not find check underscore 4 equal to OK, this cell will remain blank. Next it will check shear underscore check underscore 1 underscore way underscore F1 underscore X and shear underscore check underscore 1 underscore way underscore F1 underscore Z. If it finds both the checks are OK, it will say OK, otherwise, it will say check. Next is the check for bending in the X direction in cell I46. The defined name of the cell is bending underscore X underscore F1. Here, Excel will first check underscore 4. If it does not find check underscore 4 equal to OK, this cell will remain blank. Next, it will check the following conditions. MU underscore BD underscore 2 underscore X underscore F1 less than or equal to MU underscore lim underscore BD underscore 2. XU underscore D underscore X underscore F1 less than or equal to XU underscore max underscore D. PT underscore pro underscore F1 underscore X less than or equal to PT underscore lim. PT underscore REQ underscore X underscore F1 less than or equal to PT underscore lim. PT underscore pro underscore F1 underscore X greater than or equal to PT underscore REQ underscore X underscore F1. If Excel finds all of these conditions to be true, it will say OK, otherwise, it will say check. Next is the check for bending in the Z direction in cell J46. The defined name of the cell is bending underscore Z underscore F1. Here, Excel will first check underscore 4. If it does not find check underscore 4 equal to OK, this cell will remain blank. Next, it will check the following conditions. MU underscore BD underscore 2 underscore Z underscore F1 less than or equal to MU underscore lim underscore BD underscore 2. XU underscore D underscore Z underscore F1 less than or equal to XU underscore max underscore D. PT underscore pro underscore F1 underscore Z less than or equal to PT underscore lim. PT underscore REQ underscore Z underscore F1 less than or equal to PT underscore lim. PT underscore pro underscore F1 underscore Z greater than or equal to PT underscore REQ underscore Z underscore F1. If Excel finds all of these conditions to be true, it will say OK, otherwise, it will say check. After performing all these checks, next is the check for the overall design of footing F1 in cell K46. The defined name of the cell is check underscore F1. Here, Excel will first check underscore 4. If it does not find check underscore 4 equal to OK, this cell will remain blank. Next, it will check the following conditions. Area underscore F1 underscore check equals OK. Punching underscore check equals OK. Underscore 1 underscore way underscore shear underscore check equals OK. Bending underscore X underscore F1 equals OK. Bending underscore Z underscore F1 equals OK. If Excel finds all of these conditions to be true, it will say OK for the safe design of footing F1. Otherwise, it will say check, for making the necessary adjustments in footing F1. With this, we have completed the design of footing F1 and are entering Chapter 5 of this program for the design of footing F2. Let's go. Now, we are on Chapter 5 for the design of footing F2. Once again, we are seeing that the cells ranging from A50 to G50 are filled with dark gray, as if they are waiting for the inputs for the design of footing F2. The defined names of these cells are as follows. Cell A50, defined name LX underscore F2, it is the length of footing F2 in the X direction. Cell B50, defined name L underscore Z underscore F2, it is the length of footing F2 in the Z direction. Cell C50, defined name bar underscore dia underscore X underscore F2, it is the bar diameter of footing F2 in the X direction. Cell D50, defined name spacing underscore X underscore F2, it is the bar spacing of footing F2 in the X direction. Cell E50, defined name D underscore F2, it is the overall depth of footing F2. Cell F50, defined name bar underscore dia underscore Z underscore F2, it is the bar diameter of footing F2 in the Z direction. Cell G50, defined name spacing underscore Z underscore F2, it is the bar spacing of footing F2 in the Z direction. On close observation, we can see that these defined names are similar to those for footing F1. The only difference is that instead of F1, we have to write F2. So, with the help of the most popular method in the computer world, copy and paste, and by changing the defined name from F1 to F2, we can develop this table easily. To save your valuable time, I am not going to explain all of these points individually, except for the input check for F2. Now, I am going to explain the input check for footing F2 in cell F57. The defined name of the cell is check underscore 5. Excel will first check underscore F1. If it does not find check underscore F1 equal to OK, this cell will remain blank. Check underscore F1 is the overall design check for footing F1. Next, using an and or logic condition, it will check whether any of the following required inputs are missing. These inputs are as follows. Length of the footing in the X direction, LX underscore F2. Length of the footing in the Z direction, LZ underscore F2. Diameter of the bars in the X direction, bar underscore dia underscore X underscore F2. Spacing of the bars in the X direction, spacing underscore X underscore F2. Overall depth of the footing, D underscore F2. Diameter of the bars in the Z direction, bar underscore dia underscore z underscore f2. Spacing of the bars in the z direction, spacing underscore z underscore f2. If Excel finds that any of these valid inputs are missing, it will type provide inputs, otherwise, it will type O.K. With this, we have completed the design of footing F2 and are entering the final chapter of this program, which is chapter 6. Let's go. Since we have already crossed the 1 hour mark, we are going to hold off on chapter 6, auto-generated table for final design statement, for now. Today, we wrap up our long journey through part 3 of the strapped footing design. We can finally see the shore. We are just one episode away from reaching our destination. In our next and final episode, I will walk you through this chapter in detail along with a live trial of this complete design sheet. My heart believes a gift is waiting for me at the end of this journey. Are you not interested in sending a token of appreciation for honest, hard work? If you found this tutorial valuable, please don't forget about my gift, hitting the like button, sharing this video link with your fellow engineers, and subscribing to the channel for more advanced technical content. Your wonderful support is what keeps me going, allowing me to create these deep dive automation guides for our professional community. Thank you so much for staying with me and watching this video right until the very end. See you in the final episode.